So let's do a polynomial approximation for a few different common math functions. But in the self-driving car example, we were given the derivatives like here's the current velocity, here's the current acceleration. Now we have to figure them out for ourselves. We also have to decide where we want to focus. Let's keep focusing at 0 for now, and then later we'll focus somewhere not 0. But now we have to figure out these derivative values for ourselves, which means we have to take the derivatives using formula-based methods. So let's do the same table thing as we did before. So we'll list what derivative number we're on. 0, 1, 2, 3, let's go all the way up to 4 at least. And then the mystery column we had last time, we'll say that's our derivative formula. So what is the 0th derivative of e to the x? It's e to the x. You could say that's our f, and then f prime is the first derivative of e to the x. E to the x, there's a reason I chose this one for our first one to work with. What's f double prime? That's still e to the x. F triple prime, still e to the x. F quadruple prime, still e to the x. That's sometimes written f with a superscript 4, but it doesn't mean take the fourth power, it means take the fourth derivative because it's in parentheses. So that's our derivative formula. What's our derivative value now? Well, when is now? Well, we're saying x equals 0. So what's e to the 0? That's 1. Here, plug in 0 for x. You get e to the 0, which is 1. You're going to get 1 in each of these. And then what's our polynomial term? So let's think back to what we had on the other video. This, we just had a 1, you could say. That was like our 3 meters. And then we had the velocity, which in this case is 1, times t, or here it would be x. And then acceleration of 1 times, what was it? 1/2 x squared, or t squared. And then how about this one? Still be a 1 there. And then remember we had 1 over what? 3 factorial x cubed, or t cubed. And then following the pattern here, 1 times 1 over 4 factorial x to the 4th. And we could, if we wanted, write a 1 over 1 factorial here, x to the 1, and a 1 over 0 factorial, x to the 0. You can write them there if you want to. I left space for them, but you don't have to. It's pretty clear what the pattern is here, so we'll just say etc. And then what is our polynomial approximation? It's just adding up that whole column, right? I mean, I kind of put pluses there already. You don't really have to write them. Let's write it out in one long line. You don't have to, but sometimes it's kind of nice. We could say our polynomial approximation is 1 plus x plus 1 over 2x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th. And it's not really clear, do we really want to say etc. or just call it at 4th order and say we're done? What name would you give this? If we just stopped at the 4th derivative, you could say p sub 4 of x. Kind of squeeze that in. Let's write that better. P sub 4 of x. Just say, hey, I took 4 derivatives here. So if I had only done the first part of this, the constant term plus the linear term, then we would say that's a first order approximation because I took 1 derivative. Even though it has 2 terms, I only took 1 derivative. So we'd say it's first order. If I took 2 derivatives, so the 0th derivative, the first derivative, and the second derivative, we'd call that a second order approximation, etc. So what we have here is a 4th order approximation. So order tells you how many derivatives you took to get this polynomial. well, it's not exactly how many because we had a 0th here, so you could say which derivative was the last one you did. So which derivative is the highest derivative that you did? Is that the order of is that the degree of the polynomial? Well, if that multiplier here, that 1, had been a 0, then we wouldn't have had an x to the 4th term, so the degree would have actually been 1 less. It doesn't seem like an issue here, but it is later, so we'll just say, what's the degree of the polynomial? That's going to be less than or equal to the order of the work we did. There's no way I could get an x to the 5th if I had only done 4 derivatives, for example, because I'm always going to be matching the power on the x with whatever derivative I took. So we just did a bunch of algebra. Do we have any confidence that it's right? Maybe we should go check it with a graph. All right, here we are. We've got our main function e to the x in red. I've got a first order approximation called P1 for first order. That's 1 plus x, so that would be a tangent line, right? And it looks like it's doing a good job approximating the function near x equals 0, which is where we design things to be a good approximation. And then let's show the second order approximation, which is basically just the first order approximation plus the quadratic term. So instead of retyping the 1 plus x here, I'm just saying, well, use that function. So that's in orange now, and we can see that the orange curve stays closer to the red curve than the blue curve is to the red curve. For a good chunk of it near here, but over here, this is running away quadratically, so that's actually not so good. But right near 1, where we're focusing all of our attention, it's pretty good. And then if I show the third order approximation, the purple curve here, does that look even better than the orange curve? Yeah, it's staying closer around here, right? It's only kind of 1 grid square away, where this is 2.5 grid squares away. And it's so close, it's even hard to see the difference up here. And then if we show the fourth order approximation, that's staying even closer to the red curve, the original over here. And it's basically so close to the red curve up here, we can't really see the difference at all. So apparently our system for doing polynomial approximations has worked pretty well here, and we should go try it on some other functions.